Welcome to Brain Vision.
Okay, we have a problem here dealing with the magnetic force on a current. In this problem, we have a conductor that's sort of set up like this. We have a circular current connected to this flat current in the x direction. And we also have a current that's coming in from out of the page. So a current IN, which also has the same length L as the straight segment over here. And what we want to find out is what is the total force on this due to this magnetic field B that's pointed in the x direction. So that is part A here. So we're going to do this piece by piece. So I'm going to call this straight segment here just part 1. I'm going to call the circular part 2. And then this thing coming from out of the page, part 3. Okay, so first off, this straight segment pointed in the x direction. What we'll use here is this equation. So the force on a current due to a magnetic field is the current times the length crossed with the magnetic field. Now here we see that the current and the magnetic field are both pointed in the x direction, right? One's pointed in negative x, the other one's pointed in positive x, but since they're both in the x direction, this is going to be 0, since the cross product between two vectors pointed in the same direction is 0. So now we can move on to part 2. So here, now we have to consider the fact that this vector, this L vector, is going to be changing over the entire conductor, right? So let's think about this, right? So when we are on the right side here, the current is going to be pointing upwards. And so if we do like a right-hand rule here, that means that the force is going to be going into the page, right? So that'd be like an F2, a DF2 on the right side here. However, if you look at the left side, the current's going directly downwards, right? And so that means that we're going to get a force out of the page, DF2. And these two are going to be exactly equal to each other since they have the same angle with the magnetic field B, and the current and the magnetic field are also the same at these two positions. And so what this tells us is actually that this force, here I'll call this F2, the first one is F1, this force, F2, is also 0, right? Just due to the symmetry of the problem, right? If we pick this here, right, current just randomly somewhere on this semicircle, we can pick the same point reflected over here, and we'll find out that they have the same magnitude of force, but opposite directions, and so they cancel out. So we don't need to do any calculus for part 2, thankfully. Part 3, though, we do actually have a force in this case, and for this, we'll just simply use IL cross B to find this out. Okay, so this is the equation we want to use. So we can express this just plugging in the unit vectors. So this is going to be I times the length times the strength of the magnetic field times the cross product of their directions. So L in this case is pointed in the negative z direction, negative k hat, and B is pointed in the positive x direction, so a positive I hat here. This cross product, as it turns out, is in the negative y direction, and so this ends up being negative ILB j hat. So this is our final answer, since the other two parts don't contribute to the force at all. Okay. Part B. Part B asks what happens if we replace this semicircular part with a straight line. does the total force remain the same? And the answer is, of course, yes, right? Because we found out that F2 is equal to 0, right? And also F1 is equal to 0. So by the same argument, right, that part of the current would be pointed in the direction of the B field, and so there would still be no contribution from that part if we replaced it with a straight line instead.